The story I'm going to tell today is a rather mysterious story about the Moonshine relation connecting on the one side some special functions with special symmetries and on the other side certain finite groups. And this story is going to play out in the background of K3 compactifications. So first, let's recall that in 2D sigma models, we use strings instead of point particles to probe geometry. And when the geometry is a K3 surface, the theory actually has n equals 4 superconformal symmetry on both the left and right moving side. And with this amount of supersymmetry, we can define the elliptic genus, which is defined in terms of Hilbert space trace on the Ramon Hilbert space in this way. And it has a few nice properties. First of all, it counts BPS states, and in such a way it is holomorphic. Second, it transforms nicely under SO2Z transformation, which is the mapping class group of the underlying worldsheet torus. And thirdly, it is topological, so it doesn't care about the tiny details of the manifold. Okay, so we now compute the K3 elliptic genus using the properties we just said. So it can be written down in terms of theta functions in this way. But the symmetry algebra of the theory, namely the superconformal symmetry, suggests another way to write this function, which is to split it into two parts. The first part naturally comes from the massless multiplets of n equals 4 superconformal symmetry. And the second part, morally speaking, comes from the infinite tower of the massive multiplets. So in terms of equations, the first part is given in terms of this mu function, the so-called upper Lurch sum. And the second part comes in the form of an infinite Q series. And in 2010, these three gentlemen made a really remarkable observation, which says that these numbers, which count the number of massive multiplets, are also the dimensions of certain irreducible representations of a certain interesting finite group called M24. It is truly remarkable, and among other things, it suggests that this group is acting on the Hilbert space of the theory, at least the BPS states. So why? We want to understand why. One might guess that there exists a certain very symmetrical K3 with M24 as its symmetry. No, but we know actually the symmetries of K3s are too small for that. But we also know that K3 sigma models also have stringy symmetries that do not have origins as classical symmetries of the geometry. So you might hope that it's big enough to explain M24. But as we see, it is at the same time too big and too small. So why? The question persists. The short answer is we don't have a precise answer yet. And at the same time, there's plenty of work from both the CFT side as well as string theory side, which points to the conclusion that it's not just a coincidence that we're seeing. So it is an active topic of research to try to understand, to try to answer this question. Some of the key ideas include that we need a new way to organize the BPS states and to study its symmetries in a different way. And we need to unravel certain hidden symmetries of K3 compactifications. So now you might ask the question, why should we care? Well, first, one can hardly overestimate the importance of symmetries in theoretical physics. And second, BPS state, BPS spectrum is a very important element in string theory in order to obtain exact results. Third, from black hole counting to string duality, we need K3 compactifications everywhere. So if there is a hidden symmetry of the BPS states of the K3 compactification, we should understand it. And last but not least, it is an elegant and important mathematical problem involving number theory, group theory, algebra, and geometry. So we hope to use string theory to solve this mathematical puzzle. Okay, so in the next part of the talk, I would like to discuss some results obtained with these two gentlemen from a slightly different angle. It is often fruitful to first understand the mathematical structure of your problem. So in its essence, the observation is actually on this infinite Q series and on this finite group. So one might ask, what is this Q series anyways, and what is this finite group? And the very short answer is that this Q series is actually a Mach module form, and this finite group is an example of a sporadic group. So what are these things? Well, first recall what a Mach module form is. It is a holomorphic function that transforms nicely under SO2Z. And the very nice and simple example is given by this function. First, it is invariant under SO2Z. Second, it has a very simple behavior when Q goes to 0. And in fact, it is possible to show that these two conditions, the modularity property and the pole property, is enough to fix this, this function. And as the name suggests, a Mach module form embodies a variant of the same concept. Right now, the holomorphic function is no longer modular. It is only modular after you add a non-holomorphic piece, which is given by this other function that's called a shadow. In other words, the shadow is the function that controls the modularity of a Mach module form. And apart from its very rich mathematical history, it also shows up in physics from the following two origins. First is a geometric origin. So this anomaly of modular invariance often comes when you have a non-compactness in your problem. So for instance, when you have walls of modular stability, or you're just studying a non-compact theory to start with. And the second origin is an algebraic origin. For instance, in the example we have seen that we get a Mach modular form because we're computing the characters of certain extended superalgebra. So those are modular forms. Now let's go back to the group. What are sporadic groups? Well, according to the classification, all finite simple groups come in infinite families apart from 26 that appear sporadically. So they're the oddballs. So as we see, there's a M24, which is fairly large. And the second famous example is the so-called monsters. It gets its name due to the number of elements it has, which is as large as the number of atoms in the solar system. So as such, we can summarize our observation in abstract terms as an observation between a Mach modular form and a sporadic group. Phrased in this way, it's very reminiscent to something we might have seen before, which is the monstrous moonshine. It's an observation on this very simple modular form. That's the J function we talked about earlier. And the observation is, again, that the Fourier coefficients are suggestive of representations of the monster group. So different from the present case, after 15 years of hard work, people have actually understood the origin of this mysterious monstrous moonshine relation. So the relevant physics theory here is when you compare 5 bosonic strings on a special lattice of 24 dimensions that is called the Leech lattice. The Leech lattice has very interesting symmetries that brings you almost to the monster group. On the other hand, because when we compute the partition function, we get a modular symmetry, a modular symmetric function that's nothing but a J function. In other words, we have here the worldsheet symmetry leading to the modular form and the space-time symmetry that leads to the monster. So when you don't have this physical theory, this connection looks very mysterious. When you do have this physical theory, it's not so mysterious anymore, and that's what we're striving for. Okay, so after this analogy, we might ask the following question. Compared to monstrous moonshine, where the J function is uniquely fixed by two simple properties, why are we looking at this Mach modular form? And on the group theory side, the presence of monster group can be understood to a large extent as symmetries of the lattice. So why this M24? Okay, let's now answer these questions. So one first encouraging sign is that M24 itself is also a lattice symmetry. More precisely, it is a symmetry of the so-called Niemeyer lattice, one of the 23. So what are these Niemeyer lattices? Well, it can be constructed in the following way. First, let's look at the AD simply laced root systems. If you have 5 minutes, you can sit down and convince yourself that there are exactly 23 unions of such ADE root systems that satisfies the following two conditions. First, the rank has to sum up to 24. And the second, each component has to have the same Cossiter number. So then you obtain this list. You get some obvious ones just by combining A1s and A2s and some more interesting looking ones combining, for instance, D16 and E8 and so on. So the root lattice you obtain in this way is in general not self-dual. But you can show that by adding points in a smart way, you can obtain for each case, each of the 23, an even self-dual lattice of 24 dimensions. And in fact, they're the only even self-dual lattice in 24 dimensions apart from the Leech lattice we have seen before. And now, as we said earlier, we can just define a group by studying its symmetries. Apart from the M24 case that corresponds to the simplest A1 case, if you go to the A2 case, for instance, then you get another sporadic group, the so-called 2.M12. Okay, that's all very fine. Now let's look at the forms. In fact, so first, what's the modularity property of this guy? As we said before, it's fixed by shadow. And in this case, the shadow is given by 24 times eta to the cubed, where eta is the dead-looking eta function. Okay, and it also has the simplest possible pole when q goes to 0. And the first thing we have shown is that, in fact, this function is also uniquely determined by these two conditions. So that's pretty reminiscent, again, of the J function situation. That's satisfying, but now we're getting greedy. We want to know why the shadow and not anything else. It turns out that there are certain mathematical results that we can use to map any ADE root system to a special function. And under this map, 24 copies of A1 simply is mapped to 24 copies of eta cubed. So it is very suggestive that the shadow has something to do with the root system. So now, nothing can stop us from applying this map to other 22 cases. And now let's be brave and ask the question whether we can find Mach modular forms with this special function as a shadow for other 22 cases. And we also apply the analogous pole condition. And after a few months of work, we have found them all. And a deep mathematical theorem also says that it's unique. So that's all very gratifying. So on the more technical notes, I'll say that actually what you get is a vector of Mach modular forms. And the number of components is given by the Cossiter numbers. And often it would be natural and convenient to use, instead of a vector, actually one single function, but now with one more parameter. Okay, so we played the whole game with Niemeyer lattice. Now let's look at the functions corresponding to the second simpler case, the A2 case. And look at its Fourier coefficients. A miracle happens. Again, these numbers are dimensions of irreducible representations of a certain finite groups. That's nothing but the symmetry group of the underlying Niemeyer lattice. And you can check other cases, it's all true. So what we have here, just a short recap, we have 23 Niemeyer lattices. We look at its finite group, and then we construct in some mathematical way the Mach modular forms, and they're related to each other. Let's recall that the construction really has nothing to do with each other, so this is really surprising. So we get a new type of moonshine. We call it the Umbral Moonshine, now relating Mach modular forms and finite groups. And the 23 cases, as we have seen, has a uniform construction. And in more technical terms, what we conjecture is that for each case, you have an infinite sequence of representations whose characters give the coefficients of the Mach modular forms that we constructed. And now remember that we step into this because of the initial observation on the elliptic genus. So you might ask the question, what about the other 22 cases? Given the uniformity of the construction, do other 22 cases also have a similar physical and geometric context or not at all? So in the next part of the talk, I'll report some results in this direction. So first, let's take a closer look at our construction. We fix the Mach modular forms. The most non-trivial ingredient is to fix its Mach modularity that's given by a shadow. And the underlying mathematical theorem is actually the same results that leads to the AD classification of n equals 2 minimal models. So we might ask, is there any physical origin of this procedure? So as Kuru reminded me a while ago, that this classification can actually be understood through the classification of AD surface singularities. So these are the singularities that a K3 surface can develop. Locally, they look like a simple orbifold. And their resolution gives rise to rational curves with intersection pattern given by the corresponding AD root system. And as we have seen, for instance, in Wolfa's talk, these rational curves play an important role in physics. So maybe it might suggest that the AD root system have something to do with the rational curves. So now let's look at the other part of the construction. So the finite groups are directly determined by the lattice by studying its symmetry. But so the key question here is, do these lattices play a role in physics and geometry? So since 2011, Nick Wooling has been advocating a framework to use Niemeyer lattices to study K3 geometry. In particular, he proved that depending on the shape of your K3, or it's the Picard lattice more precisely, every single K3 surface can be marked by at least one Niemeyer lattice. And there are many non-trivial consequences of this marking. The first one is, for instance, the rational curves of this K3, the smooth rational curves, have to correspond to a subdiagram of the corresponding root lattice. And the second is that the symmetry of this K3 is then naturally embedded as a proper subgroup of the corresponding lattice symmetry group. For instance, if you look at the orbifold model, the Z2 orbifold model of K3, you get 16 copies of A1 singularity, and the only choice you have among 23 Niemeyer lattices is the 24 A1 ones. You can't embed it in any other Niemeyer lattice. And while you take the Z3 orbifold lattice model, then you get 9 copies of A2, and you don't have any other choice but to choose the 12 copies of A2 Niemeyer lattice. And in this way, the symmetry group of this K3 is naturally a subgroup of the corresponding Niemeyer finite group. So what we get is actually now 2 stories attached to the Niemeyer lattices. The first one is a geometric one, and the second one is just from Umbral Moonshine. And the different components are related to each other in this intricate way. Now, it's very tempting to sort of relate the 2 conditions, the 2 stories. But to make sure that we're not just freely associating, we should compute. So thanks to a lot of previous works, it's possible to compute the elliptic genus of the AD singularities. And indeed, they're all Mach modular forms because the non-compactness of your problem. And the first nice thing we observed from the answers we got is the following. So although the two functions are written in very different ways, there's actually an identity equating the character of a massless multiplet of the n equals 4 superconformal algebra and the elliptic genus of an A1 singularity. So with this knowledge, let's look back again at our initial observation, which splits an elliptic genus into two parts, a part from the massless multiplets and the other part from the massive multiplets. So another way to write it is actually to interpret the first part as coming from the 24 copies of A1 that's dictated by the Niemeyer lattice. And the second part is the contribution from the Umbral modular form that we have constructed from in a very different way. So notice that by doing this, we're replacing the algebraic origin of the mockness with a geometric origin. Good, so one reason to prefer the second way is the following fact. We check that the second equation actually holds for 23 cases of Umbral Moonshine. In other words, for every one of the 23 cases, you have a specific way to split the elliptic genus into two parts. The first part coming from the singularities or the rational curves as dictated, or just the root systems of your lattice, for instance. And the second part, contribution from the modular forms that we have constructed. So it's rather encouraging. You might say that, okay, indeed, all 23 cases are related. But the very non-trivial check is really only when you compare the way the same group acts on the geometry on the one side and the function on the other side, because those two have a priori nothing to do with each other. So to make this comparison, remember that for any symmetry of any K3 surface, we can write down the corresponding twining elliptic genus by just inserting the group element generating the symmetry into your trace. So this you can compute. People have computed it. And on the other hand, there's a second way of computing the twining that's suggested by the previous slide, which just comes from how the same finite group acts on Umbral Moonshine representations as dictated by these construction of modular forms. And indeed, we show that this identity holds for all such elements G that has this geometric interpretation, and for all 23 cases. In other words, all geometric symmetries of all K3 sigma models, or actually all K3 surfaces here, are captured by Umbral Moonshine. As a result, we're now positive that indeed all 23 cases of Umbral Moonshine are related to K3 surfaces. So what have we learned so far? First, this observation is really pointing to a veritable Moonshine story sharing a lot of mathematical features as monstrous Moonshine. Second, it's really a lattice story. Niemeyer lattices play a central role. Third, it's really a K3 story. Moreover, we have learned that the rational curves should play an important role. And clearly, there's a lot to explore, especially in the context of K3 compactifications. And we believe that eventually this will lead to an explanation of the Umbral Moonshine to start with, and to the discovery of many novel features of K3 compactifications and how BPS states in these theories are organized, and so on. So I thank you for your attention.
Thank you, Miranda, for the beautiful presentation. If we have time for a question.
Yes, there is a generalization of the Niemeyer lattices to CFT, which gives you about 71 cases, including the monster module. Have you thought about the possibility that that might play a role in the story?
Well, me and my collaborator, we thought about it for like a day, and then so no, the answer is basically no. We're aware of the results, and we're interested in a possible connection, but we haven't explored them.
Any other question?
So in your latter half of the talk, you mentioned you subtract the contribution from 24 A1 singularities elliptic genus out of the K3, but is there a K3 with 24?
Yeah, great.
A1
That's a great question. The answer is definitely no, because we know huh? Yeah, but if you know what it means, the stringy sense, please let me know. But an idea that comes out of Nikuling's work and is actually also plays an important role in the work of Taormina and Venlam from 2011 to 2003 is the following: is that when you move around the moduli space, okay, you're marking by the Niemeyer lattice also change. So you sort of, for instance, at one point you have a certain embedding of your cohomology lattice, sublattice, into Niemeyer lattice, and at the other point you have another one. So glued together, when glued together, they have shown that the symmetries just explode. Yeah, because group generates differently. So I think the same thing holds for the rational curves. Like with different gluing, you actually sweeps out different 16. So, and yeah, we should talk about that later.
Any other question? Yes.
So probably you have discussed it at some point, that maybe I could ask again anyhow. So 24-dimensional lattices and 20-4-dimensional lattices are playing a role here, but you didn't try to connect them in any way?
No, yeah, so that's actually close. That's another very confusing point, and that's closely related to Yuji's question, because the part that you embed into the Niemeyer lattice is only the Picard lattice part, or actually the part of the Picard lattice that have definite signature. So at least in Nikuling's story, which inspired our work a lot, it's also only the sublattice in this at least 19-dimensional, at most 19-dimensional sublattice that gets glued into the 24,0. But somehow, yeah, 20 plus 4 has to equal 24 in some way, but we don't know.
Any other question? Any question from the balcony? No? If not, let's thank Miranda.